Okay, so in today's session, we'll be discussing about the electrical introduction. Okay, so in this session, we'll be discussing about the basic like the voltage, current, power, and the load calculation we'll be discussing today. Okay, so first thing, can start with the current first. Okay, so current is actually what's actually a flow of charges. And so we know we have two type of charges. There is positive charges there, then we have negative charges there. And the charge always flows from positive to negative side. Okay, so this flow of charges, the charges from the positive to negative side, that's called what? Current. Okay, and the unit of the current is ampere. Okay, and it will be denoted with the capital A. Okay, and the instrument which is used to measure the current is called ammeter. So we'll be getting the readings in what? Ampere, and the milliampere will be getting the readings for the current. Okay, so first thing, the flow of charges is called current. Okay. Then next is the voltage. So voltage, so the definition goes like this. The potential difference between two charges is called voltage. Okay. In order to simplify, just term it like this. It's actually called the electrical pressure. So I already mentioned that the flow of charges is called current. So there should be a pressure to what? For the flow, right? So that the potential difference between the charges is called voltage, and the unit of the voltage is volt, and it is denoted by V. And voltage, again, the instrument used to measure the voltage is called voltmeter. Okay, so that's the voltage. And again, voltage we have two types. There is AC voltage is the then we have DC voltage. AC means alternate current, and DC means direct current. Okay, and let's see what's the difference between the AC and DC. Okay. So when you take the sine wave, so this is the voltage and this is the time. And when you take a DC voltage, it's actually stable. So there is no fluctuations in what? As the time goes by, there is no fluctuation in the voltage in DC current. And when you come to the AC, you can see that there is always fluctuation will be there. So it will be starting from here, then it will go to the negative half cycle. Then from here it will again come to the zero. Okay, this will be zero. Okay. Then again it will go to the positive and it will touch the top. Then again it will come back to zero. Then again it will go to the minus level. So this fluctuation always occur in the AC voltage here. Okay. So if you consider here, this is a starting point. Okay. And it will complete one cycle here. So this is the completion of one cycle. Starting from here, then it will go to the negative side. Then again it will go back to the top side. Again it will end here. So this is one cycle. Okay. So one cycle is equal to 1 hertz. Hertz means the frequency. Okay. So normally in India, we'll say the frequency of the current is 50 hertz, right? You might have seen on the unit or the equipments, everything. Okay, for 15 watt or 230 volt, 50 hertz. So hertz is actually the frequency of the AC voltage. So 50 hertz means in 1 second there will be 50 cycles. So like this, 50 cycles will be completed in 1 second. That means that's called 1 hertz. And one cycle is equal to 1 hertz. In 1 second, 50 cycles will be completed in the AC voltage. So that's what the frequency refers to. Okay. So these are the two type of voltage we have, AC and DC. And second thing is AC voltage cannot be stored. AC voltage is only used for what? Only used for transmission purpose only. Okay. For example, the power which you are getting or the power which you are using in your house for the lighting, for the fan, for any appliances, for any electrical appliances, we are using what? AC voltage. Okay. DC volt again nowadays DC voltage equipments are available like BLDC fans, brushless DC motor fans. So In that one, DC power is there. Okay, but commonly or majorly all the components will be working in AC itself. Okay, and DC example is battery. Okay, the power which you are getting from battery is what? DC. Okay, because DC can be stored. We cannot store AC voltage. It can be only used for transmission purpose only. But DC we can store that one. Okay, so that's the difference between these two. Okay, so clear? Any doubt in this one? The voltage part. Okay. Now again, we have discussed these two. Then again, AC have what? One more sub classification, that is single phase and three phase. Okay, and how to identify if your house is having a single phase connection or three phase connection, or where to get or when to get the single phase and three phase connection. So let's consider if you're having a building. In that building, the total connected load is less than 5 kilowatt. Okay, less than 5 kilowatt. So total connected load means you'll be calculating all the load of the equipments, like whatever equipments you're using, like light, fan, TV, mixie, AC, whatever components you are using in that space in your house, you will calculate the total load. If the total load is less than 5 kilowatt, you will be getting single phase connection. Okay. If it is more than 5 kilowatt, okay, 5 kilowatt, it will be three phase supply. That's what it will be. Okay. So you don't have to do this one from the electricity board. You will get the supply. So if the total control is less than 5 kilowatt from the EB, you will be getting a single phase connection. More than 5 kilowatt, you will be getting a three phase supply from the EB. Okay. And in single phase connection, the supply voltage will be 230 volt. Okay. And in three phase connection, the supply voltage will be 415 volt. Okay, and you might have seen the transmission line, for example. Okay, so you'll be hanging the transmission line. So normally the transmission lines will have what? Four lines will be. Actually, it will be five. Like, so for now, I'll just draw four lines. Okay, and one more is actually for the street lights and everything will be hanging separate line. That's I'm not including that one. I'm just including the four lines here. Okay, so the four lines will be phase one, phase two, phase three, and our neutral. This is how the line will be. Okay, so the phase one, phase two, phase three is written as R by B. That's a color code we are using for three phase connection in India. Red, yellow, and blue color code. Okay, so for the three phase, you'll be having four lines. So three phase and one neutral. So total we have four lines. Okay, and if your house have a three phase supply, sorry, single phase supply. Okay, so just draw one here. Okay, suppose this house is a residential space. For this particular space, I need to provide a single phase connection. In that case, I will take the connection from the transmission line from the R phase and the neutral. Okay. Then if I have one more house means, again, I have one more house. It's also having single phase connection. So that I'll take the next connection from the Y phase and the neutral. Okay. Again, if you have one more, so that I'll take connection from the next phase, the B phase and the neutral. So that you can see in single phase, you have only two lines, one phase and one neutral. So that we can see that in single phase supply, we will call it phase voltage. Phase voltage means the voltage between one phase and a neutral. Okay. So it will be always will be 230 volt. Okay. So the voltage between one phase, not one phase, any phase. Okay. It can be R and neutral and Y and neutral and B and neutral. So any, it will be 230 itself. Okay. And why we are taking connection like this means if I take all the connection from R phase will have the overload. So in order to balance the load, we are taking for one house I'll take from R phase, next connection from the Y phase, next from the B phase. Again, if I have one more house, again I'll start with R phase once again. So that's how you normally provide the connections. Okay. So clear the phase voltage, how it is done.
Clear, sir.
Okay. Now we have the three-phase connection. Okay, so three-phase connection. Okay, I'll just draw here itself. Okay. Same transmission line we have. For this building, I'll just take a three-phase connection. For three-phase connection, we have to take from all the lines. Okay. So I have to take one line from R phase, then Y phase, B phase, and neutral. So we'll have four lines. And here we call it line voltage. Okay. Line voltage means the voltage between any two phases. Okay. So it can be with R and Y or Y and B or B and means blue and red. Okay. So voltage between phases is called line voltage. Voltage between phase and neutral is called phase voltage. Okay, clear. And this will be always 415 volt. Okay. And normally when you see that or in the catalogs, data books, it will be 440 volt. 440 it will be written, but in the actual scenario, you don't get 440. There will be some transmission losses. After the transmission losses, you'll be getting what? Around 410, 415 volt you'll be getting. Okay. So I hope this one is clear. So shall we move on?
Okay, sir.
Okay. Now, next is power. So power, for simply one example I'll give. If you consider a fan, ceiling fan, or a tube light, it will be written 10 watt, 20 watt, 30 watt. So that's the power consumed by that element. Okay. So that is actually the power. The energy consumed by a object or a unit is called watt, the power. And it is watt, and it is denoted by capital W. And again, power has three classification. Okay. That is apparent power, active power, or you'll say true power also, then reactive power. So three classification for power. Apparent power means the maximum power which you are getting. One example. Yeah. So here you can see that I have written for single phase connection, the maximum load will be 5 kilowatt. Okay. So if your total connection load is less than 5 kilowatt, you will get single phase connection. That doesn't mean you can use up to 5 kilowatt. You can use. Okay. You can use up to 5 kilowatt. If your load goes above 5 kilowatt, you have to change to what? Three phase. This means 5 kilowatt is the maximum power which you will get in single phase. That's the apparent power. So in this condition, our apparent power or the maximum power which you can utilize is 5 kilowatt. But in daily scenario, we don't use what? 5 kilowatt. You will be using 3 kilowatt, 2 kilowatt, depending upon our activities. It may change. Okay. So the power which we are consuming is called active power or true power. 5 kilowatt is the maximum, but you don't consume 5 kilowatt. You'll be using a 3 kilowatt daily. So the 3 kilowatt is your what? Active power or true power. Okay. And reactive power. Third one is a reactive power. Reactive power, this one is considered as loss. Okay. So like every transmission loss you'll say, like that power also will have what? Some amount of loss. That loss is considered as the reactive power. Okay. So here a small representation given is funny one. That means a glass is given, a bare glass. In that one, apparent power means what? The maximum power. So that means we can fill up to the maximum level. But we are only consuming up to this level. Okay. And this part will be considered as loss. That's it. So apparent power is the maximum power, active power is the power which you are consuming, reactive power is the power considered as loss. That's it. Okay. Now, okay, so we already written this one. Okay. And one more thing, one thing to forget. Apparent power unit will be in kVA, that is kilovolt ampere. Active power unit will be in kilowatt, and reactive power will be kilovolt ampere reactive. Okay, so why we have three units means in order to distinguish between these. If you see in kVA, that means it's the apparent power. If you see the unit in kilowatt, that means the active power. If you see the unit in kVAr, it's the reactive power. That's it. Okay. And okay, so these things we already discussed, the three type of power. And one more we have, that is the forward power and backward power, second classification. Okay. Forward power means the flow from source to load is called forward power. If you are considering a source, so for example, the transformer, let's consider transformer as a source. From the transformer, the connection is, or from this transmission line, the connection is going to the building or to the space. So that means it is from the source and this will be the load. This is called forward power. Okay. And backward power means, see, is the from the load to source, then source to load. Okay. Now let's consider a circuit. Okay, a circuit here. So if we have a battery, from the battery we will run to the equipment. Again, it will come back to the load here. So from load to source, from source to load. That's it. So circuit will be the backward power here. Okay. And next is the power triangle. So power triangle is very modern because here we have discussed about the reactive power, active power, and true power. But we have a separate equation to what find out the reactive power, apparent power, and active power. Okay, so we have to formulate that equation. For that, we are using this power triangle. Okay, so concept is simple. So you can consider a right angle triangle. So the right angle triangle, this angle, this angle will be considered as the phi. This phi is called power factor. Okay. Power factor, normally we will consider the power factor as what? A 0.8 to 0.9. So power factor means uh, there is no system which is giving 100% efficiency. So there will be a some amount of loss will be there. Okay. So this loss is considered as what? Power factor. So 0.8 means we are considering only 80 percentage. 20 percentage we are what? Considering as low. If you are considering 0.9 as the power factor, 10 percentage loss is there. 90 percentage we are considering. That's it. Okay. And here, this angle is the phi or the power factor angle. Okay. And the true power is given on the adjacent side, and the reactive power is on the opposite. And the hypotenuse side, we have apparent power. So I'm getting a bit to trigonometry here. So the adjacent to hypotenuse is cos. So that true power equation is equal to P is equal to VI cos phi. Okay. In order to simplify this one, I'll just come back to the power, voltage, and current equation. Okay. So voltage, current, and power we already discussed. By these three, we can form an equation. We are all familiar about that is what P is equal to VI. That is power is equal to voltage into current. Okay. So in order to simplify this one, so it's P and voltage and current. Okay. So if you are finding out the power, that means P is equal to VI. If you want to calculate for voltage, voltage is equal to P by I. Okay, P by I. And if you are calculating for the current, I is equal to P by B. So that's way you can formulate or you can easily formulate the equation. So here P is equal to VA, that is power is equal to voltage into current. This equation we'll use for single phase connection. Okay. For three phase connection, a slight change. P is equal to root 3 VI. Okay. And from the same, you can also calculate the equation for the current also. That is I is equal to, that means I is equal to P divided by V. That is power by voltage for again for single phase connection. For three phase, it will be I is equal to P by root 3V. Okay, so this will be the equation for three phase connection. Okay, so these are very important relations. The power is equal to VA equation. So the same equation we have what using here as well in order to find the power. But here for true power, it will be P is equal to VI cos phi since it is adjacent by hypotenuse. Okay, and this is opposite by hypotenuse. That means P is equal to reactive power is equal to VI sin phi. Okay, and apparent power as usual will be P is equal to VA itself. Okay, so that's how you formulate the equation for true power and reactive power. For now, just understand this concept. In coming classes, we'll what discuss more. When you come to the APFC panel calculation and everything, we'll go in detail. Okay. So just for introduction, I'm just introducing the formulas. Okay. So that's our what power triangle. And this one I already mentioned. That's the supply voltage selection. So if you have a 5 kilowatt, you'll be having a single phase connection. That is 230 volt will be there. 5 to 100 kV will have three phase connection. Okay, so three phase connection will have 450 voltage and above 100 kVA load. Okay, if the total connected load is above 100 kVA, we don't get supply from what directly from the EB. That means you have to buy a dedicated transformer for our building. Okay, then they will give 11 kV supply. That 11 kV we can step down, then we can what distribute. So that's what it will be. Okay, so for these two will be called LT side. LT means low tension side. From 11 kV to 11 kV and above, it's called ST side, high tension side. Okay. And if you consider a residential building, you'll be having only LT side only. But in commercial space, you'll have what? Both ST and LT. Okay. So clear? Any doubts?
Clear.
So moving on to the next one, that is our maximum demand equation. Maximum demand equation is a very important equation we'll be using throughout our electrical session. Okay, so equation is to convert the kilowatt to kVA. That is kilowatt from kilovolt ampere. For that, we are using this equation. Okay. And here you can notice one thing. I have written 5 kilowatt. Then next is 5 kilowatt is given to 100 kVA. It's not given in kilowatt. Why? Because more than more than 100 kVA, we'll get 11 kV supply. And the transformer DG, these are available in kVA rating. Okay, so the conversion is very important. Okay, if you want to calculate for a ampere rating for a MCB, MCCB, or a transformer DG, for every selection criteria, we have to convert the kilowatt to kVA. So that's why this will be important. Okay, first thing, maximum demand in kVA is equal to total connected load in kilowatt. So this one will be calculated based on your load in your building. Okay, so we'll calculate the total load of every equipment you are using. That's the total connected load in kilowatt it is divided by diversity factor into power factor. So first thing, diversity factor. So let's see what is diversity factor. Okay. Diversity factor refers to the what condition that building is. So we have two conditions. That is, one is variable load condition. Second is constant load condition. So these are the two conditions we have for diversity factor. And how to decide? Okay, for example, if you are considering a residential project, okay, in residential project, we'll consider as variable load because if you have a certain connected load, for example, let's say 6 kilowatt is the load of that building, but every day we don't use what 6 kilowatt. Will be in the morning it will be 2 kilowatt, at the noon it will be 5 kilowatt, at the night it will be 1 or 2 kilowatt. So the load is varying. It's not constant. Okay, so the load will always vary by time to time. That's why the commercial projects, not every commercial project, like office spaces, everything will be considered under variable load condition. Where residential, commercial, and office space will be what? Under variable load. Constant load means, for example, if you consider a pump, if you turn on, if the pump capacity is 5 kilowatt, so from the starting to ending, the pump will be consuming 5 kilowatt cell. So it will not change in between. So this type of load is called what? Constant load. Or if you are considering a 24-hour working industry, that will be also what? Constant, because the load is not changing. Again, small fluctuations will be there, but the load will not vary that much. So based on these conditions, we are selecting whether the building is variable load or constant load. Okay. If it is variable load, we will consider a constant from 1 to 2.5. Okay. And for the variable load, we'll take from 1.5 to 2.5. So we can consider between 1 to 2.5. But for variable load, we will consider between 1.5 to 2.5. And if it is constant load, we will consider the value as 1. Okay. Now, next is power factor. Power factor, we all discussed, it's what is the ratio of active power to apparent power. This was the power factor. Okay. So the power factor we can consider from zero point 0.8 to 9.5. Often we'll consider what? 0.8 as a power factor. Okay. So yeah, these are the parameters we have for the maximum demand equation. Okay. I can start with a small calculation. Okay. So I'll just do one small example. Convert 4.5 kilowatt to kVA. Okay. Okay. So it's a residential load. Okay. So I have to convert the 4.5 kilowatt to residential load. Okay. Now, okay. So here total control is given. Total control is uh, total total connected load is 4.5 kilowatt. So you can see that it's 4.5 kilowatt. That means what kind of load it is? It's a single phase connection, right? Single phase connection. So load below 5 kilowatt is single phase, above 5 kilowatt will be three phase. So here it's 4.5. That means it is a single phase connection. Okay. So we have the total connected load. Then we have to consider what? The diversity factor. Okay. So diversity factor, it's a residential load. That means it will be a variable load condition, right? So that it's a variable load condition. So that it will be 1.5. Okay, so that's what we have discussed here. If it's variable load, okay, the range is from 1.5 to 2.5. Just consider 1.5 as what? The constant for the diversity factor. Okay, then the power factor will consider as 0.8. Okay. So power factor, that is 0.8. So we got all the parameters we require for our equation. Okay, I have the total connected load. Diversity factor we got based on our variable condition. Power factor will be 0.8. Clear? Okay, now coming to the equation, that is maximum equation is equal to, that is total total connected load by total load divided by diversity factor into power factor. Right, this was our equation. Okay, so just what substitute our equation, that is equal to total control is 4.5. So 4.5 divided by diversity factor is, just open a bracket, 1.5 into 0.8. Okay, close the bracket. So that is 3.75 kVA. So that's the answer. Okay. So our conversion value of 4.5 kilowatt to kV will be 3.75. Okay, got it. How we calculate? So do you need to do one more example or this one is fine? Okay, so I hope this one is okay. Now, next we got the kVA. So kVA, this is the power we have. Okay, so once you got the power, you can what? Calculate the ampere rating also. So we already have the equation, that is what? Equation is P is equal to VI. Power is equal to voltage into current, right? And in order to find the current rating, current means I is the current. Okay, so equation will be I is equal to P divided by V, right? So that we have to, okay, I is equal to P value. Now, power is 3.75. Voltage, how to calculate the voltage? You can see that it's a single phase connection. For single phase connection, the supply voltage is 230 volt, right? So just what? Substitute 230 volt here, then you will get the ampere rating, right? So that just consider here, it is I is equal to, okay, so I, that is equal to P. P is 3.75 equal to 3.75 divided by voltage is 230. Okay, so just divided by 230. And one more thing, this is 230. Denominator is volt. So 230 volt is here. and the numerator is in kVA, that is kilovolt ampere. So we have to convert this kVA to volt ampere itself. Okay, because the denominator will be in numerator is kVA, denominator is in volt. So if you convert the kVA to VA, the V and V will cancel, and the final you will get in what? Result in ampere. Okay, so we have to convert the kVA to volt ampere. Just what? Multiply with 1000. So the 3.75 into 1000 it will be. Okay, just open a bracket. Then divided by 230, that is what? 16.3 ampere. So this is the ampere rating. So 3.75 is the kVA rating. 16.3 is what? The ampere rating. So this is how you find the power and the current rating for a system. So very important equation we have to use throughout the session for this one. Okay. Clear? Any doubts in this one?
No, sir.
Okay. Anyway, I'll just do one more. This is for the single phase connection. I'll do one for three phase connection. Okay. Let's see how it will be. Convert. Okay. Let's consider a 25 kilowatt. Okay. 25 kilowatt to kVA. Okay. One we have done for variable load. Let's consider a constant load. I'll just give a motor load. Okay. So convert 25 kilowatt to kVA. It's a motor load. So let's analyze the conditions. First, we have total connect load. Total connect load, that is 25 kilowatt. Okay. That means it's a three-phase connection. It's a three-phase connection. Now, diversity factor. Diversity factor, the condition I have already given, it's a motor load. That means it's a constant load condition. Okay. Constant load condition. That means one will be the diversity factor. Then power factor, as usual, will be 0.8 we can consider. This is the first condition. So we have the parameters we have. So let's what? Continue with the maximum equation. Maximum demand equation, that is total connect load. Total connect load is 25. Okay. Divided by its diversity value is 1 into 0.8 is the power factor. Just close the bracket. And that is 31.25 kVA. Okay. Now the current rating. Okay. So equation again, P is equal to VI for single phase, but for three phase it is what? For three phase it is root 3. Okay, root, I have to add the symbol. Okay, so root 3 VA. This is the equation, right? So root 3 means 1.71 itself. So you can add that for calculation, or simply you can what? Add root 3 also. No issues. Okay. So that equation is root 3 VA, and I is equal to P by root 3V. Root 3 V. So that's the equation for the current rating. Okay, so we have the parameters we have. And for three-phase connection, the voltage will be 450 volt. Okay. Now, coming to the equation, I is equal to P. P is 31.25 divided by root 3. Root 3, I'll just write as 1.732, okay, into voltage. Voltage is 450, so I'll just write 450, okay, close the bracket. And one more thing, again, it's given in kVA, so we have to convert the kVA to volt ampere. Just what? Multiply the 81.25 with 1000, okay. So once you enter 43.47 ampere, okay. So yeah, that's how you calculate the ampere rating for a three-phase load. Okay. Single phase and three phase, again, concept is same. Only the equation has slight change. We'll add a root 3 here. Then the voltage will be 450. That's it. Okay. So yeah, that's it. Our maximum demand and our power calculation. Okay. So clear, any doubts?